Hello and welcome. Here I will be tackling a new concept about integrals. As you can see, we have a given function f represented by this curve, and we will take 2 points, variable points. Let's take this point, for example, of abscissa x1, a given abscissa, and another point on the curve such that the distance between the abscissas of these 2 points is h. So the other abscissa will be x1 plus h. Okay, and of course, since our function is named f, so the ordinate will be respectively f of x1 and f of x1 plus h. Okay, now the question here, or the concept, is how to determine the area of this region. Okay, I will color it in red. So how to determine this area, okay, named A. Okay, so we have to determine this area. It's a very interesting idea and method. First, we can bound this area between two other areas that we can calculate the areas like rectangles, because this shape here, the shape of this red area, is not defined. We cannot calculate its area directly. Whereas if we take this shape, for example, it's a rectangle. Okay, so it's the purple rectangle here. We will name it R2. Okay, and we will take also another rectangle. Let's choose another color, example blue, and this rectangle, okay, R1. So the small rectangle in blue is R1, and the bigger rectangle in purple is R2. Of course, it's obvious here that our area A is bounded between R1 and R2. Okay, so we can write this. The area is bounded between R1 and R2. Okay, I can put equal or equal here, because for some cases, in some cases, maybe the area is equal to R1 equal to R2. Okay, for example, if the curve is like this one, for example, okay, so here in this case, the area of the shaded in red A is the same as the rectangle if we have this case. Okay, so we can write or equal. Now, after writing this bounding of A, we can also write A in a different form. Let's see together. The area A is equal to the area of the whole part between O and x1 plus h. Okay, I will shade it in green, this part. Okay, minus the small part in gray, this one. Okay, so if we subtract all the part below the curve from from 0 to x1 plus h, which is in green, minus the part from 0 to x1, from O to x1 in gray, we will get exactly the area we are looking for, which is A. So we can write A as A of x1 plus h, and we mean by A of x1 plus h the whole area between O and x1 plus h, so from here to here, all this area, and minus the area between O and x1, this part, we will denote it by A of x1. Okay, so that's A. A of x1 plus h minus A of x1 is equal to A. Now, the area of the two rectangles. Okay, what is the area? Here we are, of course, interested in the area of R1 and area of R2. The area of R1, which is the blue rectangle here, okay, this rectangle. What is the area of R1? We know rectangle, the area of a rectangle is base or length times width, right? And the length here is h. Okay, it's h because x1 plus h, so the distance between x1 and x1 plus h is h, times the width. The width is this height, which is f of x1. F of x1. Okay. Now the area of R2, the rectangle in purple, same method. It's h multiplied by, this time, f of x1 plus h. Okay, so we get this inequality, and by a simple procedure, if we divide all of them by h, because we know as that h is a real number, a positive real number. So if we divide all of them by h, we get a new inequality. I will copy this one. Okay. Okay, so that's the new inequality. So if we simplify here by h, we will get f of x1 less than a of x1 plus h minus a of x1 over h less than f of x1 plus h. Okay, so that's the new inequality. Back to the previous page, here in this figure, notice here that to get a perfect, if you want, perfect shape or perfect area, the distance between x1 and x1 plus h must be very small. Okay, so if h is very small, we will get approximately a straight segment here. Okay, so we will get this segment. which is the distance between the curve and the straight line. Okay, so suppose that x1 is here. Let's take just to clarify it. For example, if we have this curve and here is x1, okay, so if h is almost 0, we will get this segment, which is perfectly the distance between the curve and the x-axis. Okay, then for h equal approximately 0, it's the perfect area here. But notice here, if we calculate the limit of all of these when h approaches 0, okay, so if we approximate h to 0, we will get the limit f of x1 when h approaches 0, okay, and here the limit of all of that, a of x1 plus h minus a of x1 over h when h approaches 0. Let me erase this. Okay, and at last, limit f of x1 plus h when h approaches 0. Okay, of course, limit f of x1 when h approaches 0 remains f of x1, because f of x1 doesn't contain h at all. And limit f x1 plus h also will give f of x1, because if h is approaching 0, we'll get f of x1. What is interesting is here, the limit of a of x1 plus h minus a of x1 over h is in fact the derivative of a of x1. Okay, so it's the definition of the derivative. It's the how to test if a function is differentiable. Okay, limit f of x plus h minus f of x over h when h approaches 0. So this limit is equal to a prime of x1. Okay, what can we deduce here? We can deduce that f of x1 is equal to a prime of x1. Okay, and consequently, if a prime of x1 equal f of x1, then the area, okay, of x1 is equal to the integral f of x1 dx. Okay, so that's how we can prove the relation between the area and the integral.